So, dear colleagues, it's my pleasure to introduce Marcin Moszyński from Warsaw. Warsaw. Yes, he will give a talk. Where is the title? On the spectral theory of cyclic operators and related topics. Yeah. Okay. Yeah. Spectral theory for self-adjoint cyclic operators and its analogs for finitely cyclic ones.
Okay. Thank you very much, and first of all let me thank all the organizers, all the administrative staff, also in Euler Institute, organizers of the Spectral Theory and Mathematical Physics program. And I would like to say thank also because it was really very, very difficult to come here, and I was the first time here 5 years ago, and it was my dream to come back here. And now during these COVID times, really I thought it will be not possible. And at the last moment we managed to get the visa, and not only me but also my family came, and it was very big help of all the organizers here, so I'm very grateful to everybody that I can be here. So this is my mini course. I would like to say that it's dedicated to the memory of Sergei Naboko, not only because he died half a year ago, but also because he was a very important person for me. I met him more than 20 years ago in Krakow. He was then invited by my elder colleague, Professor Janas from Academy of Science from Krakow. When I met him, he lived for several months in Krakow, in the Institute of Mathematics of Polish Academy of Science, the Department of Krakow. I started then the collaboration with Professor Janas with Jacobi matrices. And Professor Janas asked me to give a long talk on the seminar from operator theory about subordination theory for Jacobi matrices. So it was my beginning, I can say, in this subject. And I didn't know anything about Sergei. I saw a very nice person, and slowly we started to be quite good friends, and we started to meet very often in several places, also to spend the time not only for mathematics but for singing, for instance, also, and I can say also that it was a very difficult time for me. My father died half a year ago, and later I realized that Sergei died just, I think, 2 days later after my father, who was also a mathematician. Yes, and the subject I will talk about is also somewhat related to Sergei. I will tell you about it. The reason I decided to write now a manuscript. I plan to publish it in a form, I don't know which form, and my lecture will be, I can say, from this manuscript. I will just make a shorter version of the manuscript, and the manuscript I will give you the scan of the manuscript to read, because of course I will not be able to tell everything, for instance all the proofs. To make the introduction about the subject and about Sergei, I should first write the definition. Let H be a Hilbert space, A an operator, possibly unbounded, in H. The definition is that A is cyclic if and only if there exists a vector in H which is not only in H but which is also in the domain of all the powers of A. This is the intersection of all the n power of the domains of all the powers of H, yes? Such that when we take the linear span of all such vectors, where n belongs to n0, maybe now for a moment I will switch it later for some notation, but now I think it's understood. n0, this is natural numbers plus 0, yes. So this space is dense in H. So this is equal to the whole H. So this is cyclic operator, and each such vector is called cyclic. Cyclic for the operator I. And when a vector is cyclic, of course, we can multiply it by a scalar is also cyclic, but usually you can have a lot of cyclic vectors. So this is general definition, and for us only self-adjoint operators will be important. So another definition for A self-adjoint. I will give another definition, not so wide. A is essentially cyclic. When we know something more about this space, we should know that this is the essential domain for the self-adjoint operator. So this linear span, I will not. Okay, this linear span, yes, is an essential domain for A, which means that when we restrict A to this domain, it's essentially self-adjoint. Yes, so this is something more than this. Yes, and what is the story? Once I talked with Sergei about this notion, and I told him that in many books some important theorems, especially the theorem I will talk about in this first part, about the unitary equivalence of such operators to some multiplication operators. So those theorems were proved in many books only for bounded operators, bounded self-adjoint operators, and the proof was almost trivial. So I told him that, it's usually written in such books that, okay, it can be extended to unbounded self-adjoint operators also. Okay, so but the question is how you can extend this. Now I told Sergei, of course, it can be easily extended for such situation. When this is true, the theorem, the main theorems are also true. And I told him, I am sure when this is not satisfied, it's not true. This is not enough. And Sergei told me, oh no, you are stupid. It's not true. This is enough. And I told him, oh no, it's impossible. And I lived I was sure that I'm right. But I feel that if Sergei told me that it's not true, that it is enough, something should be not okay. And he told me, oh, this is Stone theorem, that it should be okay. And I was quite lazy, so I didn't like to look in some books. I sometimes try to prove something. Is it enough to find an example that it cannot be true for such general case? And unfortunately, I didn't find any example. So I started to try to prove it, and I found a proof. It was not very difficult. So now I will show the proof. It will be in the first part of this mini course. I will show you the detailed proof for the general case that I will formulate the theorem, and this assumption is not important. So we can forget about the name also. Yes. This is important. Of course, I should say why I am interested in cyclic operators. I told you that I am studying Jacobi operators. So that Jacobi operator is one of the main examples of each Jacobi, self-adjoint Jacobi operator is one of the main examples of cyclic operator. And when we want to generalize and we start to study some block Jacobi operators, they are not cyclic usually, but they are finitely cyclic. And this is why I will also try to generalize the theory, this short, small spectral theory, to block Jacobi matrices, not to block Jacobi matrices, but to the case when we have not the cyclic situation, but we can write something similar, just taking not one vector, but a finite number of vectors, and write the same for finite number of vectors, and we will obtain something which is called finitely cyclic operators. And it's known, it's written in some papers. The theory you can find in some sense, but that's what we can do in such case. Yes, we should introduce a special kind of Hilbert spaces, some model spaces for such situation, so-called L2 matrix measure spaces, and we can develop a similar theory which can give us, we can say in some sense, canonical form for such operators. Yes. Okay. So now let me, if we can switch into the slides for a moment, I will only introduce the basic notation for my talk, for my lecture. It will be only the introduction of the notation. Why then I cannot switch. I don't know. Maybe, okay, something. This is. Да, это работало уже. Но уже не работает. Maybe I should switch on and off again. Okay, so let's.
Оно точно, так, может быть, мы еще раз.
I don't know. It has 3 pages. Oh, okay, some notation. It was okay. So how did you do this? Okay. Oh, and now it works also. Okay. So look for the notation. There was a stick. Nadia, nie wiesz gdzie jest этот stick. Okay. No stick. Okay. Oh, I have something like. No, we cannot see. Okay, so, спасибо. Is it good? So, I will use this letter for the identity function on R. These are natural numbers with 0. This is the space of complex D by D matrices. And for a matrix A, I, J, this is the term of each row and J column of A. Now, the shorter notation for...
They will use laser pointer.
Here?
Yes.
Maybe yes. Oh no. Yes. Okay. Shorter notation for LP spaces. When we have a measured space, so mu is a measure, this is a sigma algebra and the set. So I will use such a notation instead of such a long notation for the space of complex functions. So this is not the Banach space because this is we don't have a norm here but a semi-norm only. So this is just a set of the space, linear space of functions, yes? And this is the appropriate space of classes of complex functions. I will distinguish between those two things. Usually mathematicians don't do this, but here it will be better to distinguish, yes? Because for matrix measure situation it is important. So to start to distinguish it for matrix measure, it's good to distinguish it. It's also for measures. And we shall use different measures, so it's also important because of this.
What is the difference?
The difference is this space consists of functions. And this is the space, the Banach space. So two functions which are equal almost everywhere are the same in the same class, yes. And here usually we forgot about this, yes. But the same will be important for matrix measures, and it's better, and the notation will be similar, and this is better to remember the difference. So this is why I will use this, and this is, I will call this calligraphic LP, mainly L2 I will use, and this will be capital LP, yes? And the classes I will write, so it will be an element of calligraphic space, and this will be the class which is obtained from an element, yes. Okay, and this pole or from polynomials with this new on R, it will be the subspace of this space, yes, of classes of all the polynomials for a Borel measure me on R. I will use this also. So this is just a subspace.
Excuse me, what does it mean, polynomials for the Borel measure?
When we have, when we have a Borel measure and we have, and we have such a space, but this Borel measure is on R, we can consider all the polynomials, just the usual polynomials, and sometimes for some measures, not for any measure, but for some measures, each polynomial is in this space, yes? So then we take the classes of all those polynomials and we obtain just a subspace, a linear subspace of this, in this case, yes? Simply this, okay? Of course, it is not possible for any Borel measure, because we should be sure that each polynomial is of the A2 class. Yes. Okay, so this is just the notation. Okay, and now some other notation. So when we have the space, I consider here several types of space. Scalar product space, semi-scalar product space, where we have a semi-scalar product. So here you can see, this is the typical notation for the scalar product here. But sometimes we don't have a scalar product, but something which I will call semi-scalar product, just when we don't, when it's not degenerated. For instance, in those calligraphic spaces, the usual scalar product is not just a scalar product, but a semi-scalar product. Yes. So I will use this double brackets in this case. dA is just the domain of A, and such an operator for L2 of mu spaces will be the operator, usually unbounded operator, of multiplication by a function, scalar function f. Now here only for such spaces, and then also for those general matrix measure L2 spaces. I will talk about them the next part. And now some notation for spectral measure. When we have so-called spectral measure, I mean I use the name spectral measure for or the resolution of unity for so-called also projection valued measure, yes, spectral measure, projection valued spectral measure. So when we have a sigma algebra M, just for any M A of omega is the appropriate orthogonal projection in X. It should, to be spectral measure, it should satisfy several well-known, I hope, conditions. And when we have a spectral measure and we have two elements, X and Y, from the Hilbert space, this will be the appropriate complex measure, which is defined like this. Yes, just by taking the value on X and then taking the scalar product with Y. And this is a short notation for this, when here and here we have the same the same x, and this is just the finite measure. This is the measure, not only the complex measure, so this is non-negative. And when we have an operator A, which is self-adjoint, we know that there exists so-called spectral measure for A, which is defined on Borel sets, yes, and then we'll use the notation like this. This is the same, but for the spectral measure of the operator A. Yes, and for instance, this will be called, this is something like this, but for A equal to EA, I'm sorry, it was every time E, not A, yes, okay, and this will be called the spectral measure for A and the vector X. Okay, something more? Okay, it will be used during the proof, but now let us switch to the blackboard, okay. So I will formulate the main theorem, and I will sketch the proof. So this is our main theorem for today, we can say. So as I thought, it probably comes from Stone, but nobody is completely sure. I will call this xMUE theorem. MUE, yes, thank you very much, theorem. X, because this is multiplication by x, just by the identity function on R, unitary equivalence theorem. Yes. So it has two parts. One is, we can say, general, and then some details. If A is cyclic and self-adjoint in H, sorry, in the Hilbert pair H, and phi is the cyclic vector, acyclic for A, then A is unitary equivalent to the operator of multiplication by x, by the identity function, in the space L2 of mu, where mu is equal to the spectral measure, just to the spectral measure. I showed you the notation of A and this is A, E, A, phi, yes, for this cyclic vector, yes. So there exists a unitary equivalence which changes this into just the very simple operator of multiplication by x. And what is important, that we assume only that this is a cyclic self-adjoint operator. We don't assume that this is essentially cyclic, but only this. Yes? And now the second part, which is sometimes also important. Moreover, point one, okay, this space polynomials of μ of R. This is a dense subspace of our space, of this space. So it's contained in this space and this is dense. The second part, there exists only one bounded operator, which is a bounded operator from, this is the notation for bounded operators, is B, calligraphic B, from L2 space, this L2 space, into H on. Yes, such that for any n from n0, u of the, and this is the class of the function x to the power n. Yes, so mononomial, we take a mononomial and the class in the space L2 for this mononomial, and it shifts. This operator shifts this class, the element of this, into just the element of the form a to the power n on the cyclic vector phi. This is the second part, and the next part, 3. This unique U the unique U from the part 2 is a unitary operator from L2 of mu onto H onto is important. Yes, this is a unitary important between those two spaces. Yes, and it is defined by, no, defined, maybe it's not good to write it defined, because in some sense it's defined here, but it satisfies. It satisfies the following condition, which can be also considered as a definition. So when we take any class from this space, any element from this, so the image of this element is just the function f of the operator a. Yes, it is a Borel function, so it can take a Borel function of the self-adjoint operator, and we can how to say, use it on the vector phi. Yes, for any f belonging to the calligraphic A2 space. So this is just a formula for this unitary equivalence, which is in the first part of the theorem. And I didn't know this, and this is important, that this is just our unitary equivalence. Yes, so this is the theorem. So now, unfortunately, I will use the second two blackboards, so we should switch. I hope everybody remembers the theorem, but I think it will be better to switch on to the second. Oh, it's not so. Okay. So I will start the proof. So the beginning of the proof is quite easy, and you will see that the proof for bounded operators is almost trivial, yes? So we define first U tilde. U tilde will be not from the L2 capital space, but from L calligraphic, yes? And everybody can guess what will be the definition, knowing this part of the theorem. It will be just given by this formula. So, yes, we define such an operator, and U tilde of f is just f of a on phi for any f from A2. And now let us switch for a moment to the slides, to the last slide. Yes, and you can see the explanation. This is just, I recall, well-known fact from the spectral functional calculus for self-adjoint operators. So when we have a Borel function, I mean, it's measurable with respect to the Borel sigma algebra on R, yes? I don't know, maybe it should be called Borelian, I'm not sure the terminology. So it's well known that in this case, the domain of the operator, the function f of a, is just the set or the subspace, we can say, of such y from the Hilbert space, that the function f belongs to the to the calligraphic L2 of the spectral measure E of the operator A for the vector y. Yes, this is the first information, and the second information from the spectral functional calculus for self-adjoint operator is the norm. So the norm of this vector f of a on y for y in the domain of it's a mistake. It should be not the domain of A. Y should be from the above domain. Yes, I'm sorry. It should be corrected. So for such Y, which are in the domain of f of A, the norm of this vector is just, we can say the semi-norm of f, or the norm of the class generated by f in this L2 space. Yes, so this is the most important thing which allows us to prove this theorem. And now we see that this is a good definition. Yes, so this is a good definition. So this vector, for instance, belongs to the domain of this operator. Yes, this is first information. So the definition of our U tilde is correct. Of course, it is linear operator, and what we can obtain. Now, of course, using this what was on the slide, we can write that when we take the norm of U tilde of phi. Let us square it. Okay. This is in H, in the space H. So this is just f of A on phi, the norm. It's everything in the space H. So this is, we just take phi equal to y, yes?
You see the f. You see the f, not phi. Here, yes.
No, this is on, yes, of course. Thank you very much. Of course, it's f. Yes. And this is just, we can take the class of f, and it will be in the space, in this space, yes. So
What is f in brackets?
though this is an element which is in L, when we take the bracket, we take the class. It means the class which belongs to the capital. Yes. So this is something what we usually omit. Yes, because we think on elements like about the functions. But I told you that I want I want this for the second part of the lecture. Yes. Okay. No, but we started later, so I should continue. So what to do? Okay. And what we can see from this formula, we also see a very important thing, that when we consider such a subspace of L calligraphic, for which we can say the seminorm of f is 0, so this is in the kernel. Yes, this is included in the kernel of utility. Yes, and this is important because what we want to do, we want to factorize this operator from this space, which is not a Hilbert space, but this is, we can say, semi-Hilbert space without the norm. We want to define an operator here on this space. So it's important for us that we can do this correctly. And this is why we can do this correctly, because from this we see that when f is 0, yes, when the norm is, semi-norm is 0, yes, so it means that this element is just 0, and then this is also 0, so this is why this inclusion holds. So having this, we can just factorize. We can just factorize, and we can write the formula which is just written here. We can define this operator, and this is the correct definition. So I will not write again this, but we see that mu defined by this formula is bounded, but not only bounded, it's also an isometry. We can see this from this formula. This is bounded, and moreover, this is isometry, but this is isometry, but we don't know what is the image of this isometry. Into, it's isometry into H. Yes? But we didn't use the cyclicity now. So, what we have, okay. We should use the cyclicity now, and what we can obtain? We can obtain that the linear, we have the linear space, linear span of all the an on phi for n belonging to n0. This is dense. This is dense in H, yes? So, what does it mean? When we have isometry, such, so now we see that the image, yes, each such an element is by the definition in the image of this isometry. So when this is isometry and the image is dense, and because this is isometry and our space L2 is a Banach space, so the image of the isometry should be also closed. So it's closed and dense, so it is just the whole H. So now we know more that U is not only isometry, but this is also the unitary transformation. Okay, this is a unitary transformation, and when we recall that an of phi, okay, we should write it down probably. We should write it that let me write this. So what we have, observe that when we have n, the natural number of 0, and we take u of the function, the class of the function x of n, what is this? This is u tilde of x of n by the definition. So this is by the definition the function x of n of a on the cyclic vector phi, yes, and on the other hand, and what is this? Oh, okay, what is this? What is it? This is just a to the power n, yes, because this is the identity function. Identity function to the power n of a, yes, this is a to the power n by the functional calculus. So this is this, yes. So we obtain one of the formulas from the assertion, yes, and when we use this and we remember that U was unitary, what does it mean about all those vectors in the space L2 of mu? All those vectors are dense in H. Form the linear spans is dense in H, and U is unitary. So it means that the linear span of all those vectors is dense in L2 space, which means just that the polynomials, this space is dense subspace of this. Yes, so we proved also this. Yes. Okay, so this is also true, but first we don't know that this only one is true, but we know that there exists because we constructed. But why only one? No, now it's obvious, because when we assume that we consider all the continuous operators, and we know that these vectors forms its linear span is dense, so by continuity it should be also unique. Yes, so this is also true, and we know this also. So the last thing we should prove is just this, and this is the second part of the proof. And what we can write.
At
Yes, but it's a question we started later.
Yes, we started.
I would like, if I can,
We
spend.
have that is 45 minutes.
So you want the break now?
45 minutes.
Yes, I know.
Then the second break and another 45
So
minutes.
would you like to have a break now or next, or in 10 minutes, for instance?
No.
If now, it's better now. Okay, so let's make.
So we have 10 minutes break.
Okay.